Assalamu alaikum. Today we shall talk about the current in semiconductor. The current is because of the movement of charge carriers. Suppose we have a number of charge carriers, each has charge q and they are in motion. The velocity of the carriers may be different to each other. Now if we multiply the charge with the velocity of the charge carriers and we sum over all the charge carriers, then we will have the electric current. This is same if you calculate the current from the total charge q flowing in a time t, then I would be q by t. This should be the same as that one. Now we know in semiconductor there is a partially filled conduction band and a partially empty valence band. So we want to calculate the current in each of the band. So let's start with the conduction band. We will have very small number of electrons here. Now if we just sum over the electrons, we consider all of the electrons, then we will have the current from the conduction band. Here q equals 1.6 into 10 to the power minus 19 coulomb. So minus q is the charge of the electrons. Now we can do the same for the valence band, but the problem is this is almost full and hence it has a huge number of electrons. So we want to simplify it so that we don't have to sum over the huge number of electrons. For that, we can write it like this. So the current, there's a current in the valence band can be written as like this one. This is summing over all the states minus the empty states, because we now see that at room temperature the valence band has some empty space because some electron transfer to the conduction band due to thermal excitation or photon excitation. Now we know that this doesn't contribute to the current. This doesn't conduct because this is full. This is represent the field valence band, and we know when this band is filled, it doesn't conduct any current. Also at the same time, when the band is completely empty, it doesn't conduct. To conduct, the valence band have to be some empty space. So this minus multiplied with this minus, then we have the sum over the empty space. This is the charge of hole. So the charge of the hole is opposite to the charge of the electron, but this is same. Now the current, as we see here, depends on the motion of the charge carriers, also depends on the charge of the charge carriers. That means it depends on the amount of carriers. So in semiconductor, we know we have electrons and holes, two type of carriers, and both lead us to a current. Now the current could be because of two reasons. One can be the drift current because of electric field. We know in the conductor, when we apply an electron field, the electron tend to drift in following the direction of the electric field and causes a current. So the current in the semiconductor can also be because of that. This can also be because of diffusion, and this happens when you have a non-uniform carrier distribution. That is, if you have electron here and the other place there are less number of electrons, then electrons from one place where it has higher number is tend to diffuse to the other place where the number of electron is less. So the current can be because of drift current or because of the diffusion of the carriers. Now, if we assume the velocity is to be the v of the carriers, the average velocity could be because of the drift or could be because of diffusion, then we have I equals q by t. As I told you, this should be the same as the previous calculation. Now the t should be the total length divided by velocity. If we have a system of length L, then this would be the current. But in physics, since the current depends on the length, we tend to use the current density, which is independent of the dimension of the system. So we defined current density J equal current divided by the area, that become the charge divided by the volume multiplied by V. So this is the density or the concentration of the carriers. So this we write it rho. Now if every charge carrier has a charge Q, let's say all we have is electron, it's minus Q then, and the concentration is, if we have n number of charge carriers, then we multiply, then we replace rho equals minus Qn, then we have the current density equals minus QnV. Now, in order to know that how much current is flowing in semiconductor, we need to know how many carriers we have, and we also need to know how fast they are moving. We can see is from here that how much carriers we have and how fast they are moving. And to answer this question, we actually need to know the number of available state in the conduction band and the probability of these states are occupied, because we know at 0 Kelvin the conduction band is completely empty. Now as the temperature increases, it tends to occupy some of the states in the conduction band tends to occupy from the electron coming from the valence band. Now that's why we have to know what is the probability of each state in the conduction band is being occupied by electrons, and also at the same time how many states or levels are there in the conduction band. Now to answer this, actually for the first question we need to know density of state. That is actually the same. If you see is the how many states we have in the conduction band, we since the conduction band, size of the conduction band could be different to one system to another, we simply said the density of the states in the conduction band. And the probability of the states are being occupied is given by the Fermi-Dirac distribution or Fermi-Dirac probability function. Once we know these two functions, we can answer these two questions. That means we can calculate the current in the semiconductor. Now the density of states is the number of states per unit volume per energy. So this is actually represented by G of E, and this is called density of state. In some other text, you may find this is written as D of E. So this is also written. And when we multiply the density of state with dE, that means the number of state per unit volume in the energy range E and E plus dE. So this is, if we write it in by definition, will be like this: the density of state, number of state in delta E divided by delta E and volume. This is the density of states. So to know the density of state, we need to know the number of energy states in the energy band. If you do the calculation, which we are not showing here, the expression for the density of state should be like this, And you can see this depends on the effective mass of the electron or the carrier, and it depends as the half power or the square root of the energy of the band. So this is a typical structure of the band, density of state. So as the energy increases, density of state increases. This is the gap, and then we have higher band. Now the Fermi-Dirac probability function has this form. This is the EF is the Fermi energy. We will talk about the Fermi energy in a second. So this actually gives the probability of a state in the conduction band being occupied or empty. So it actually looks like this at 0 Kelvin. So this is where I'm plotting here E minus EF at 0 Kelvin. So if T becomes 0, then the shape of this should be like this. It will follow this one. Let's see. So it will be like this. That means at 0 Kelvin, all the states are filled. So you can see that the Fermi level is the value of the top filled shell at 0 Kelvin. Now, as the temperature increases, you can see there is a drift. So this is filled. This is empty at 0 Kelvin. Some electrons tend to go from the filled state to the empty state. So that there is a deviation of the shape from the 0 Kelvin. And this is obvious because at 0 Kelvin, for semiconductor, the valence band is filled and the conduction band is empty. As the temperature increases, number of carriers or number of electrons tend to transfer from the valence band to the conduction band. And if you have higher temperature, you have more electrons in the conduction band. And this shows the same. Now, if we integrate the product of this density of state and the Fermi-Dirac distribution or Fermi-Dirac function for 0 to infinity, we will have the number of the carriers, that is concentration of the carriers. Remember, this is energy, number of states per unit volume per energy. So we have number of carriers per unit volume. That means this is concentration or the density of the carriers. Now, the Fermi energy that we said that we will talk about, this is as the highest occupied energy level for a material at absolute zero temperature, that is at 0 Kelvin. So the shape is something like that. For insulator, this is in the middle between the empty conduction band and the filled valence band. This is also same for intrinsic semiconductor, but for a semiconductor, the gap is less than the insulator. For a metal or conductor, you know that the band is half filled, so Fermi level is in the middle. And for a p-type semiconductor, it is close to the filled conduction band. And for an n-type, it is close to the, this is for p-type, it is close to the valence band. And for n-type, it is close to the conduction band. So you can see gray here. That means we have some carriers here. This is n-type. Okay, and I think this can be understood better here. So here I didn't show that the different types. This is just intrinsic semiconductor. For the metal, it's in the middle. For the insulator, the gap is higher than the semiconductor. So just to show an example, for the insulator, since the Fermi energy is in the middle between the conduction valence band and conduction band, if we integrate up to the Fermi energy, we will have the concentration of the carriers. That means in terms of the concentration of carriers, if we integrate the density of state from 0 to Fermi level, we get the Fermi value, just to simplifying this one. Here I don't have f of E because f of E is 1. This is at 0 Kelvin, of course. The f of E is 1 for the conduction. This is because these are all occupied, so the probability is 100%. These are all empty. So I'm integrating only for the occupied states. So this is how we can calculate also for the semiconductor, for the conductor also. That's all for today. Thank you.